Hi, I'm Professor Goins. In this video, I'm going to look at a proof of the fundamental theorem of calculus part 1. Start with the statement of the theorem. This says that if f of x is a continuous function, then if I were to define this integral from a to x of f of t dt, so notice that I have the variable x in my upper limit of integration. If I were to differentiate that integral, the result would be the function f of x, the continuous function that we are starting with. Said differently, this integral from a to x of f of t dt is an antiderivative of f of x. So that's the same statement as saying that the derivative of the integral is the function f. Okay, before I prove the theorem, let's look at a theorem that we have seen earlier in our course called the mean value theorem for integrals. A very simple statement. Let's look at the geometric idea first. If I have this green curve from a to b, the integral is, of course, the area underneath. Assuming that the function is non-negative, then the integral is the area underneath this green curve. If you look at this green curve, what you could imagine is I could draw a rectangle with sides starting at A and B. So I could take this, the top of this rectangle, and put it somewhere along here where the area of the rectangle exactly matches the area under the curve. And approximately here, the area of this, say, purple rectangle would exactly match the area under the curve. So symbolically, this says that the integral from a to b of f of x dx would be the function value, so the height of this would be the function value at this point c, where that point is on the graph, f of c, times the width. So this is height times width. So this is the rectangle, and this is the integral of the area under the green curve. Okay, we're going to need that statement within the proof of the fundamental theorem of calculus. All right, here's the start of the proof. Let's define what's called the area accumulation function, and the area accumulation function for this graph of f of x. So this f of x and this f are going to be the same thing. It's just a continuous function. I'm going to define the area accumulation function with base point A to be the following. It's the area under the curve from A up to a point x. You can see this is a function of x. From A to x under the graph, that's the function values for this. So the area accumulation function is the integral from A to x. So that's my starting point. All right, let me clean up. I'm going to delete or erase the statement of the theorem, and then let's walk through how the proof works. Okay. Let's start with the following quantity. F of c plus delta x minus f of c. Before I do anything with that, let's look at a picture of what that represents. F of c plus delta x would be, if I take a look at that area accumulation function, and I started at, say, A, and I go over to, let's say this is c, then c plus delta x would be to the right of that. Therefore, f of c plus delta x would be this area between starting at A and ending with c plus delta x. The quantity f of c that I'm subtracting would be the area from A up to C, where again, as a reminder, c plus delta x is bigger than that. So it would be this area right here. When I subtract these two areas, what I'm left with is the area in between c to c plus delta x. All right, that gives a visual for what this represents. So then symbolically, what this gives me when I take the difference of these two functions, this would be the integral from a to c plus delta x f of t dt minus the integral from a to c of f of t dt. So when I take this region and I subtract off this region, I'm left with just this strip right here. And that would be represented by the integral from c to c plus delta x of f of t dt. Let me summarize what I have here. So summary, just so I can get this all in the same line. I have f of c plus delta x minus f of c is equal to the integral from c to c plus delta x f of t dt. So there's the summary for what I have so far. Remember, f is the original function, that continuous function that we started with. Capital F is the area accumulation function, and we are looking at this difference here on the interval from c to c plus delta x. Look at the right-hand side of this equation then. I've got an integral over this specific interval. Well, that looks just like this right here. What that means is I can replace this integral with something that looks like this, a function value times the length of the interval. Therefore, I would have this right here would be a function value, f of k, times, so it's b minus a, that would be the length of the interval. The length of the interval from c to c plus delta x, so in other words, from c to c plus delta x, the length of this would be delta x. That gives me the function value f of k times delta x. Now, what do we know about k? Well, k just has to be, just like here, it has to be somewhere between the endpoints of the interval. So let's say k is like somewhere here. It's somewhere between c and c plus delta x. Let me write that down here so we don't forget that. I know that k is somewhere between c and c plus delta x. Well, what I'm going to do with this equation right here is let's divide both sides by delta x. We'll see what that gives us. This gives me this equation right here. Now, the left-hand side of this should look familiar. This is a difference quotient. And what do we normally do with difference quotients? We end up taking a limit as the denominator goes to 0, which gives me a derivative. That says if I take the limit as delta x goes to 0 of the above difference quotient, take the limit of the other side as well, well, what do we get? On the left-hand side, the limit as delta x goes to 0 of this expression. This difference quotient is the derivative of the function f with respect to x, evaluated at x is equal to c. On the right-hand side, well, what happens with the limit of f of k as delta x goes to 0? Well, remember what k was. K was a value between c and c plus delta x. If delta x goes to 0, then by the squeeze theorem, k has to be c. So this says that the derivative evaluated at x equal to c is equal to f of c. C was chosen arbitrarily, so c can represent any real number. That means that this derivative equals f, that means that the derivative of capital F with respect to x is equal to f of x. This says that capital F is an antiderivative of lowercase f, therefore proving the theorem, which is what the fundamental theorem of part 1 is all about. Okay. Again, the key idea was defining capital F to be this area accumulation function, and then we had to use the mean value theorem for integrals.